In question 5, we are looking at an elimination reaction. And further, we're looking at an unusual elimination, because we're told in the question that this elimination yields the less substituted alkene. So our leaving group being this iodine, the question is telling us that we get this product, and not the one that we might have expected, which would be this one. And so the question is why? Now we know that traditionally most eliminations follow Seychow's rule and form the more stable or the more substituted alkene. Now we have learned about Hofmann eliminations, which can favor the less substituted alkene. But in general, Hofmann eliminations require very bulky leaving groups as well as bulky bases. And you'll notice that while we haven't said what the base is here, the way the question is written sort of implies that it doesn't matter what base we used. But more importantly, with iodine as the leaving group, that's not a terribly large leaving group. So we can rule out the possibility of a Hofmann elimination. So what's going on then? Well, with a cyclohexane ring, always a safe bet to draw a chair conformation if you're not sure what's going on. The tert-butyl group is up, and we know that has to be equatorial. We can then fill in the iodine as well as the methyl group. How does this help us? Well, remember that for an E2 elimination, the leaving group and hydrogen that's being removed have to be 180 degrees apart. Well, if we look down at the more substituted carbon, its hydrogen is over here. And as we can see, that's certainly not at 180 degrees. In fact, that's going to be more like 60 degrees. So that means we have to go over to this carbon. Its axial hydrogen is at 180 degrees, which means it can be used for an elimination. It's just that's the reason we end up with what we don't expect, which is the less substituted alkene. Again, that's because on the other carbon, this hydrogen cannot go into an equatorial position, an axial position, because this T-butyl group has locked the ring in place.